Okay. Let's see. Number 8 should be the same for everybody. So I'm going to do a freebie for you. Anytime you get a question about, I give you a distribution and say, what percentage is between this and this, this and this? A really good first step is to put what right in the middle. So I know this is normal. Good. The mean, which in this case would be equal to the median if it really is normal, so I'll let that go. And then if you take, like, what would this be and what would that be? It's how it would be one standard deviation up, and that would be one standard deviation down. So what numbers are we talking about then? Each standard deviation is, let's see. Yeah, so this would be 143.6, and then one down would be 80.4. Sounds about right. Cool. Do you already see a number that looks familiar on number 8? A or B? Maybe B, right? We see a 143.6, so somehow that's going to relate to part B. Do I see part A's numbers yet? No, so we go no. Let's one more step down. Yeah, 48.8, and then one step up. Crazy enough, it's going to be 175.2. Let me stop right there. Is everybody with me where the hell those numbers are coming from? I like that. So, if I take one step up, and when I say step, I mean standard deviation, right? So the standard deviation, what did I do here? It's 31.6. The mean was 112. So if I take one step up, I add 31.6. Take one step down, I subtract 31.6. So I could represent this with the number 1. What would that mean?
First deviation.
It's one step up, and this would be the number 2. This is the number -1, and the mean is pretty much always 0. I like it. Does that make sense there by itself? So that's called standardizing this distribution. Oh God. I'm taking these numbers and making them 0, 1, 2 effectively. Right? It's one step away, 2 steps away. Because now, what is always within 2 steps away? If it's normal. 95. I love it. So the answer to part A is 95%. There's 95% of the stuff between this and this. You guys kind of with me? So that's a rule. That's the empirical rule. And it's related to Chebyshev. It's just a lot more specific because they know it's normally distributed. So where's most of the data in a normal distribution? Towards the middle. Right? Because that's the highest point. You with me? So the empirical rule says there's actually 68% in there. 95% within the next 2 steps. Right? 2 steps up, 2 steps down. 99.7 in the next 3. So if you're having trouble with exactly where are those numbers coming from, let go of that. Right? If you've had calculus, I can explain it to you once you see the really ugly formula that you have to integrate. If you've not had calculus, let it go. Right? So this number actually relates to the area of the shape. So 68% of the area of the shape is here. And for a normal distribution, the reason I know that number so well is because I know a normal distribution has to have that certain shape. So whatever, I don't care how skinny it is, how fat it is, if I go one step out, it'll catch 68% of the area. You guys kind of with me? So if I add this whole area up, the whole area for the whole thing, what would I get? 100%, or 1 as a decimal, right? Okay, so the whole area underneath there is 100%. 68% of that's within 1 step. 95% of that's within 2. And that's the one I wanted. It's within 2. Between 48.8 and 175.2, there's 95%. Okay, maybe. So I really desperately want you to understand it. Real quick, let me see if you guys are with me. If the mean was 5, and the standard deviation was 0.3, and I know it's normal, How can I draw this picture, the same kind of picture I just drew up there?
5 in the middle.
5 in the middle.
5.3.
Good, 5.3.
4.7.
Now stop right there. What percentage of the data must be between 4.7 and 5.3?
68%.
Because that's one step out, right? And that's the beauty of these numbers here. That's what I mean by standardizing it. If this is between -2 and 2 steps, it's 95%. If it's between -1 and 1, it's 68. So what is this? -1 because I went one step down. What's this? 1. That's always 0 because it's 0 away from itself. So whatever the hell these numbers are, I don't really care. If I change them into how many steps away they are, I know exactly how much data is in there. What percentage of the data, in this case, 68%. So that's what you mean when you say something like standardizing a test. You're making it so you can compare it easily. No matter if the mean was 1 billion and the standard deviation was 300 million. That's crazy huge, but I can make it 1 step, 2 steps, and then it just follows the same rule. I standardize it to 0, 1, 2, and then it has to follow the same rule, no matter what those specific numbers are. Okay, maybe. So that's the beauty of it being a normal distribution, and that's why so much of this class will eventually be, how do I know if I'm working with a normal distribution? And there are many tests we can run later. Because if I know it's normal, kick ass. I can use empirical rule. I know exactly how much percentage is in all these places. I love it. Now, part B deals with, somebody help me out.
543.6.
I love it. So how would I shade that in on my picture? What area am I actually talking about in that case? Yeah, from 143.6 and up, right? That's the area that part B is talking about. So what area is that? How the hell do I figure that out?
Subtract 68 minus 100. That gives you the size and then you divide it by 2.
So I know this goes up to 68, right? So if I do 100 minus that, if this is 68% inside, how much is outside? So how much is on that side?
16.
And what's the property that tells me I can just cut it in half? This thing is symmetric. I love it. Just trying to fold it on itself. You guys kind of with me? A little bit? So if I want to know what's here, that's actually outside of here. These two tails together would be 32%. So how much would that tail by itself be? Half of that. Okay? So look at this one real quick. Let me make up a problem here real quick. So what's the next step up here?
5.7.
I love it. And one more step.
5.9.
And then one step down here for 4, 4, 1. So could somebody tell me what percentage is in there?
5%.
So how many steps away is this? Yeah, 3 steps away. So how much is in here?
99.7.
Since it's 3 steps away, I know it catches almost all of it, 99.7. So what percentage is outside of there then? 0.3. 0.3%. So how much is down there then? 0.15%. I love it. So this is 0.15% is in there, which makes sense. It's tiny. Tiny little thing. So really, if I relate, let me relate it to something we're all more familiar with than whatever the hell these numbers represent. How likely do you think it is? And in fact, let me remind us, the mean height for men is 69 inches, which I found really interesting. Those of you that had father's heights, the average came out to be, I think it was, damn if I remember, 68.36 inches, roughly, around there. That's almost 69. That's pretty damn close. I like that. And the standard deviation, let's say it's 2.5. I can't remember exactly, but we'll say it's 2.5 to make it easy. So if I want to know what percentage of men are taller than, what you got, Jeff? 76.5 inches. Percentage of men, let me just go right to it. Taller than 76.5 inches. So that's the percentage that are taller than 76 and a half inches. That's how many feet in inches?
6'4.5".
Yeah, 6'4.5". So what percentage do you think? Do you think it's a large percentage of men that are taller than 6'4.5"?
No.
How many guys in here are taller than 6'4.5"? Anybody? How tall are you guys? You're my tallest guys, so I think 6'1". 6'4", exactly. Cool. So right now we have nobody in here that's over 6'4.5". You with me? And the way I've drawn it now, what goes right in the middle?
69.
69. So then what's one step up?
71.5.
One more step?
73. 74.
74. I like it. So I just keep adding 2.5. Are you guys with me? I just keep adding a step, and each step is 2.5 inches. 2.5 inches. That's almost too easy to believe. Some of you guys are like, what the hell? All I'm doing is adding 2.5. 2.5. If I want to go the other way, I subtract, right? But obviously I'm only going this way because I'm talking about that big ass number. One more time, and of course I end up at.
0.5.
So I want to know what percentage of men are in there.
0.15.
So how many steps away did I just go?
3.
So we already have the answer. We already did the work for this answer. You guys realize that? What percentage are more than 3 away? 30%. 0.3%? So 0.3%, and then half of that would be 0.15%. We've already done that work. This was just on the other side. It's symmetric, so it's the same percentage on that side. So if I made my doorways 76.5 inches tall, what percentage of men would complain that they had to duck 0.15%? So from a PR perspective, PR, what's that mean? Public relations. All right, we know it because we've been on both sides of it. From a PR perspective, I can live with that. That's not that many complaints. You with me? Airlines do this all the time. Do you sometimes get bumped? Has anybody ever been bumped from a flight? You guys are lucky. Yes? Thank you. Me too. Sucks. Why does that happen? Why do they bump people from flights sometimes? They overbook the damn thing. What the hell's wrong with these people? Why would they do that? Some people don't show up. And what do the airlines want? A full frickin' plane, right? They get this sucker in the air, they want it full to make it efficient. So they are going to overbook it. And they're going to do the statistical analysis. What percentage of the time does this many people show up? This many people. What can we live with? What's the probability of people complaining because we had to bump them? What can we live with? And then I know exactly how much to sell. You guys kind of with me? That's exactly where statistics is used. And hopefully we're at the point, if you understand this problem, you understand what I just said, and that's a direct application of this in the real world, which is always nice. It's what math students always want. Statistics was made for that. Okay. So how are we doing there? Is that decent? Because very soon, chapter 6, what really, can anybody tell me? I want you to realize this is kind of neat. Because I can tell you a pretty good guess. You know, like how many men in here are between, what's one step down?
-1.
Good, -1, I like it.
66.5.
66.5 inches. So if I want to know what percentage of men are between 66.5 and 71.5 inches tall, what would you say? 68%. So I would take 68% of the number of men in here, and that would come out really pretty good. I'm going to have to do that now and show you. A good estimate for the number of men that are in there. Because that is how heights are distributed. And is there any reason that taller people or shorter people would take this class? I can't think of one. It doesn't mean there isn't a reason, but there probably isn't. It's probably a decent random sampling of men. You guys kind of with me? So they should follow this distribution pretty well. Okay, maybe. And we saw that when we did the distributions. I don't know if you remember, they were roughly normal. It's not a huge sample size, but they were still pretty roughly normal. Okay. Whew. All right. So what I want to do today. Is there any other questions from the test that you want to talk about in general before I leave it? Anything else from the test? Okay. So just don't forget the corrections aren't due until test 2. So you have some time. All right, you can turn them in any time before then, up till then. Oh. So we have one section in chapter 3 to finish out. And then we're going to get a little bit into chapter 4. Oh, yeah. Now, let me talk about something we sort of talked about. I just haven't used this word except for in the bonus section on the test. And it's actually related to what I had up here a second ago. Let me ask you this. If I knew the mean for something was 40 and the standard deviation was 1.7, what number would you put underneath that? The way we were doing earlier? 1. And what does that represent? It's one standard deviation. So this data point is one standard deviation away from or above the mean. I love it. Right? Because -1 would be below. So as long as you say away from, I'm cool. So that's 1. What about, now here's what I was trying to get at earlier. I don't know if I actually said this. What sucks about empirical rule, there's one thing besides the fact that you have to memorize it, just get over that. What sucks about it, why is it not as powerful as we want it to be? Remember earlier I said, for men, I said that probably they were more than 76.5. Why did I pick that number exactly? Because that is exactly a number that came out when I kept adding the standard deviations. What if I wanted to know the probability that men were more than 75.429 inches tall? For some really weird-ass reason. Could I use empirical rule? No. That's not going to fall in there. It's not 1, 2, or 3 steps away. Are you with me? So empirical rule is really strong, but at the same time it's really weak because it has to be exactly 1, 2, or 3 steps away. And can't something be 1.5 steps away? Of course. Yes, it can be. Let me show you. What would 1.5 steps away be here? Can you guys figure that out? If I wanted to know what would the score be that's 1.5 steps up, can you guys figure that out? This is actually not even a statistics problem. It's more like an algebra problem. Just the wording is strange.
42.4.
How'd you get that? 40 plus 1.5 steps, right? That's the quick way to do it. I want to start at 40 and I want to go 1.5 steps up. Well, how big is each step? 1.7. So there has to be a data value that's every value in between, if you have them all, right? There has to be a height that's exactly 1.693 standard deviations above the mean. And that's not going to, empirical rule, is empirical rule going to know what to do with that? Because what does empirical rule work for? 1, 2, 3. Are you guys kind of with me? So chapter 6 is where we're going to use this idea, but they introduce it here. It's the idea of z-score. Sounds like an old 70s cartoon in the mornings, but it's not. I'm thinking about G-force, but that's too bad. Let me ask you something about this, kind of the reverse of what I did here. Can somebody tell me if my mean is 40, my standard deviation is 1.7? Can you figure out exactly how many standard deviations away 43 is? How would you do it? What mathematically would you do? I want to know exactly how many steps away that is. Don't tell me it's almost 2 steps away.
1.
How'd you get that?
3 divided by 1.7.
Where'd you get the 3 from? I'm just like, dude.
-46.
Exactly, I like it. Right? I mean, if I want to know how many steps fit in here, won't I say, well, how far do I have to go? I got to go 3 away. Right? If I'm starting at 40, I want to go 3 away, and every step I take is 1.7 big. But if I take 2 steps, I overshoot this dude. Right? I'll go too far. So if I take how far do I have to go divided by how big each step is, I'll see how many steps fit in there. That's exactly the definition of division. How many of these fit in there? Right? So if you do that, 3 divided by 1.7, you'll get the 1.76. So underneath here, I would put 1.76. The exact same way up there we put a 1. They mean the same thing. They still mean how many standard deviations away I am. Okay, so this is the z-score. Can somebody tell me, this is what I love about statistics, because you can see the formulas, how they get put together. Somebody help me out. What are the parts of this formula? What is this? That's the mean, right? So the z-score formula is going to be minus the mean. What's this? Standard deviation. So it's over the standard deviation. Now, what's this? Was that anything special about that number? I didn't even know how many standard deviations away it was. This was just some data point. And what letter do we use to represent the data points? X. So that's the z-score formula right there. X minus the mean divided by the standard deviation. How we doing? Maybe. Okay. So that's why it tells you, the z-score tells you how many standard deviations fit in between here. That's what it tells you. Now do me a favor. Do a little algebra on this. Here's the little tiny bit of algebra you need. Solve for x. Solve that equation for x. I know there's no numbers in it. This is why you took algebra before you came here. Solve that thing for x. So just to help you out a little bit, what's a good first step? Yeah, I mean, you have a fraction in an algebraic equation. You want to kill the fraction first. So you multiply by sigma. So you get z sigma equals x minus mu, and then it's one step away. Add the average. So we just write it like this. Add the average over, so I get mu plus z sigma. Now here's the thing I really hope you start to realize, in statistics especially, you should be able to read every formula in English. And this one is perfect. We already have this formula on the board. We just have numbers in it. You start at the mean, and you go this many standard deviations. Start at the mean, and you go this many standard deviations to get to the data point. Let me say it again. Any data point, you get there by starting at the mean, and you go this many standard deviations. So if a data point had a z-score of 2, how many standard deviations away is it? 2, because the z-score tells you what? The number of standard deviations away. So if I had, let's say, a mean of 10 and a standard deviation of 1.4, let me ask you a couple questions. What's the z-score for x equal to 8.9? And then what data value has a z-score of 2.37? So the big thing about statistics is knowing when to use which formula. And it's kind of a giveaway And this first one, I don't know z-score. So I want to use the formula that solve for z. So I want to use that. And do you have all the information you need for that formula? Hell yeah. I gave you the mean standard deviation, then I give you a specific data value. I can figure out what its z-score is. Even before you do this formula, is it going to be positive or negative? Is it above or below the mean?
Below.
So it's going to be negative. I like it. And is it a full step down from 10 to 8.9? Is that a full step? No, full step would be 8.6. It's not quite a full step, is it? So it should be a negative number that's less than 1. Let's find out. I plug everything I know in. What's x? 8.9. What's the mean? 10. Standard deviations? 1.4.
Negative 0.7.
I like to see a negative 1.1 divided by 1.4. Negative who what?
0.786.
786? That's fine. Does that? There's two levels to this. One is, I know it's going to be not quite a full step down. So I know it's going to be negative. I know it's going to be less than 1. That makes sense. It's not quite a full step down. Technically, it's just plugging the right stuff in the right place into the right formula. But it jives with what we thought it should happen. It's negative 0.7 makes sense. Okay? And again, would empirical rule know what the hell to do with that? No, because empirical rule lives on 1, 2, 3 steps away. So chapter 6 is where we beef up empirical rule. We just fill in all the gaps. We'll be able to handle 0.79. We got to round it to 2 decimal places, but that's all right. What about this one? How do we do that problem? Is it this? It's sort of the same as this. You could start here, but do you know x?
No.
No. So it's better to use a formula that solve for x, right? That's why the hell you have to know how to manipulate variables, is to make the formula correct for the situation. So I'd rather use this formula here. Because I don't know what x is. I can just plug everything on that side and figure out what x is. I don't have to solve for x. It's already solved for x. So what's the mean? It's still 10. Z is 2.37. And standard deviations are 1.4 big. Now you just have to do that. 13.318. Blah, blah, blah. Okay. How do you feel about that? So there's a couple of levels to this. There's, can you do the work? Can you do the algebra? Or just the straight up computation? But secondly, and almost more importantly, does it make sense? Do you know what it means? Do you know what that means? So why does this make sense? Maybe. The mean was 10. The z-score is positive, so I knew that my answer should be above the mean. It should be above the mean, not less than 10, but more than 10. And it's more than 2 steps. 2 steps would be 2.8. That would be 12.8. It should be more than 12.8. So that answer jives. So 13.318 makes sense. So the reason that they put this in this section is because this section is all about relative standing. How many guys have taken the SAT or ACT? When you get your results back, what do they look like? Do you remember? I don't know how long it's been. Like, can't remember that. But they give you like a scale, and they tell you what percentile you're in. You're like in the 89th percentile or the 40th percentile. You with me? Did you ever know what the hell that meant? If you're in the 89th percentile, that does not mean you made an 89 on the test. That's not what it means. In fact, that wouldn't be fair. Because what do they do with the SAT test every now and again? They change it, right? So you can't compare somebody who took it this time versus somebody who took it that time. You can't. So what you do instead is use a score that's going to compare it between everybody who took that test. So what's really going on is does anybody know what that word percentile means? If you're in the 89th percentile, what does that really mean?
You're in with 89% of the other people.
Say again?
You're in with the other 89% of the people that took the test. Or
Almost. You scored
higher than
89% of the people that took that test. I love it. So it's a relative score, relative to that test and those people that took it. You with me? Okay, maybe. So we're going to talk about two things. One thing is, before I get back to the percentiles, before I get too far away from z-scores, these are both measures of relative standing. It's relative to other people or relative to the data from the test. So, for example, if on your math test you made 68, and on your history test you made 83, is that 68, especially if your teacher's going to curve, is that 68 necessarily somehow relatively worse than the 83? Now, obviously, on one level, it's like, well, yes, Jeff, one's a D and one's a freaking B. What do you want from me? Right? But the z-score will measure relative to the rest of the class, how did you do? What if on the math test, the mean was 71, and the standard deviation was 11? Whereas on the history test, the mean was 88, and the standard deviation was, I don't know what you got, Jeff, 8 point, no, let's just make it 8. Sounds fine. Bunch of 8s. So now they're both below the average, but this is not very much below the average. You kind of with me? In fact, you're going to be in classes not too far in your future where 68 is a damn good grade. Because maybe the average, especially if you're taking biology or some of the sciences, because the average might be a 40. So if you got a 68, you should be very happy. That's going to be very strange for most of us in the future. Trust me, I got my first grad school test back, and I made like a 40-something, 42%. And I was like, what the hell am I doing here? I should leave. And the teacher said, good job, Jeff. I'm like, are you evil? What's your problem? But no, it's just because that relative to other people, that was not a horrible grade. So what's the z-score for this situation? So if I want the z-score, I need to know those three things. What's the x? Yeah, that's the specific data point that I'm interested in, 83. What's the mean?
88.
88. Standard deviations?
8.
Or 8 big? Yeah, there. Yeah.
40.
625, yeah. So negative 0.625. What's the z-score for the math situation? What's your x score?
68.
68. And I'll call it the raw score. That x, I'm going to call it the raw score because it's before you processed it. It's like raw sugar versus processed sugar. All right, so that raw score is 68. We're going to process it now. The mean is 71. Standard deviation is 11. Second? Negative 0.27. Sounds about right. 3 11s. Yeah. Okay. So which one's actually relatively better? The math, because it's not as much negative as this one. Now, they're both worse than average, right? But relative to the test, relative to how everybody else did on that test, the math score is actually a little bit better. There's no way you can just look at it and tell. You guys kind of with me? Okay, maybe. Okay. Now, this is why curving happens, right? This is why I had to curve that first quiz, for example. Okay. So that's what z-scores, it's one use for them. We're not going to see z-scores again throughout Chapter 4, and unfortunately also Chapter 5. But then they're going to rule our life starting in Chapter 6. Z-scores are like it for statistics. They're the place to go. Right now, you just have to know how to use that formula. Percentiles. So a percentile, if I'm in the 90th percentile, we use the symbol P90 to represent that. So if you see a big P90, that means 90th percentile. And again, like we said earlier, that means what exactly about your score? If you're in the 90th percentile, you did better than 90% of the other people. I like it. So this is 90% of other grades below you. Okay. So some of you guys are going to get this right now, and some of you guys are going to realize this later. The smaller your sample is, the less resolution I can get. Like P93 versus P94. If I have a small sample, they're going to be the same damn number. I don't have enough room to really make distinctions. So you just got to let that go. To make it easy for right now, I'm just going to use a list of 10. So we have to realize that it's a small sample. You guys tell me what your gut feeling is. I'm going to put them in order. Hopefully you realize this is a lot like median. In fact, median would be what percentile?
50?
11. So the median is the same thing as P50. Because it's the value that has 50% below it, which also has 50% above it. So P90 has 90% below it, so it has to have 10% above it. Cool. So if I had, let's say I had a quiz. Say it's out of 50 or something. One, two, three, four, 5, 6, 7, 8, 9, 10. So can somebody give me a guess as to what P90 must be? What score would be the 90th percentile?
45.
Anybody have a different opinion? Those of you who said 45, what's your reasoning?
Most.
Close to the end, I like it. So why not 43 or 49?
49.
All right, so another guess might be 49. I like it. And now here's where I can be really evil, say they're both wrong, but it's good. It's your gut would say that. But what must be true about P90 is that it has to have 90% of the data below it. So if you look at it that way, what's 90% of 10? 9. So if you have to have 9 data points below you, you must be this. But it must also have 10% above it.
43.
10% of 10 is 1, so in that case it must be this. God damn it. And really the trick here to realize is it's a lot like the median. Don't we sometimes for the median have to average two things? What's half of 4? What's half of 4? 2. Is the median the second number? Hell no, it's the average of the second and third. Are you guys with me? Median is just a very specific percentile. So the rest of the percentiles will have the same problems. So in this case, actually, to find P90, it's not either of these two, it's the average of those two. The average of these two? Yeah, good. The average is 47, is that cool? How many numbers are below 47? How many numbers are below 47? 9. 9 out of 10, 90%. How many numbers are above 47?
1.
1. 10%. So it's got both. It's got 90% below, 10% above. How you doing?
So we just add 45 plus 49 divided by 2.
Exactly. But now I want you to realize, just like with a median, you sometimes have to take an average and you sometimes don't. Right? So I want to make it very clear when you have to take an average and when you don't. You ready? You're like, whatever, Jeff. Just do it. All right. So here's the official steps to do this. So if I want to find P90, there's 2 steps. The first step is to take, now this makes sense. If my list is in order, how far do I have to go approximately to find the 90th percentile? I have to go about 90% of the way in, right? So to find P90, I would take 90% of n. And what's n in this case? I love it. In this case, it would be 10. There's 10 total numbers. You with me? So the first step would be, what's 90% of 10?
9.
9. I love it. If that number comes out to a whole number, you average that with the next one. So it's not the 9th number. It's the average of the 9th and the 10th. Are you guys with me so far? So if this number that I get on the first step, if it comes out to a whole number, I take the average of that one and the next. So an average So step 2 is go get the answer. Average the 9th and the 10th. That's exactly what we just did. 45 plus 49 divided by 2. 47.
Even if you have like 200 numbers, you still
Yep.
average 2.
Yep. So far, so good? Yes?
What if there was odd
I love it.
number of n is equal to like 9? So if it's like, if there's 9 numbers, then we don't need to average it?
You ready? So that's problem 1, is P90. So how would I find, for example, how would I find P45? What's my 2 steps break down to? For that same list of data, how would I find P45?
Take 4
Take 45
divided by 3.
I like it. So you're already there. But say it more generally. What would I do in general? Take what percent of what?
45.
Yeah, 45% of 10 in this case. And that, of course, is... How do I do that mathematically? 45% is what as a decimal?
45.
What's of mean?
How many?
Times. Good, thank God. Fewer and fewer people know that. When you're talking about percentages or fractions of something, of means multiply. I don't know why high schools have decided not to teach that anymore. Or they do and you guys just forgot. I don't know. What's 0.45 times 10?
4.5.
4.5. If it comes now, you ready? When do you average 2 numbers for percentiles? When this answer comes out to a whole number. If it comes out to anything else, you round up and take that number. So this is 4.5. I round up to... So the 5th number is the answer. Step 2, go get the answer. And the reason I want you to realize there's 2 steps is somebody will tell me the answer to this is 5. Could 5 be the 45th percentile? 5 would be way down there somewhere. It's not even up there. So 5 is not the answer. 5 is where the answer is. So step 1 is where is the answer. Step 2 is go get the freaking answer so you can tell me. Right? So what is the 5th number?
39.
Yeah. 1, 2, 3, 4, 5. So P45 equals 39. I like it. Some guys might realize, what's P46?
39.
39. P47? P42? 39. Right. Because I only have 10 data points. There's not enough to specialize for all those. You with me? But 10 is enough to get the idea across, and that's all I'm worried about right now. So there's always 2 steps to percentiles. First step, you take the percentage of how big your list is. If the number comes out to a whole number, you have to average that with the next. If the number comes out to anything else, if that would have been 4.03, I would have rounded up to the 5th number. You just round up. I like it. So how does this work with, if I want to find the median, how would I make that work look more like a percentile? 50th percentile? So my first step would be 50% of 10, which is
5.
5. That's a whole number, so what do I have to do?
Average.
Average,
5 plus 5.
5th and 6th. So the 5th and 6th are 39 and 40. 39.5. So of course, if I have 10 numbers, I have to average these 2 to get the middle number. Are you with me? We know that. In P50, if I do the work, it matches up. It has to match up. Okay, maybe. You good? Okay, so let me give you a couple of problems to try real quick, and then we're going to get a little bit in chapter 4. So here, using this data here, how many is that? 1, 2, 3, 6, 7, 8, 9, 10, 11, 12. That's pretty good. I want you to find, what you got, John? P25, P10. That's pretty good. Let's do those 2. course, be really careful. What's really nice about the lists that I'm giving you?
It's in order.
They're already in order. So if you have a list that's not in order, you got to do it first, or else your answers won't make any damn sense at all. You got to put it in order for it to make sense. There used to be some. So, I mean, there's a lot of shortcuts to this. So as long as I can tell what you're doing, I'm cool with it. If you don't see a shortcut, just do it exactly the way I'm doing. You'll be fine. Yes, sir.
So when we round, does it have to be like to the nearest 10?
If I don't say, pretty much always go 2 places if I don't say. Now, we know for standard deviation you have to go at least 3. So I said. But if I don't say on a test and I don't say in general, go out a couple places. Yeah. So what's the steps for P25?
25% of
Yeah. 25% of 12. I like it because there's 12 data points. So that's why I want to do another problem, because people get fixated on 10 and so they start doing 10 for everything. This was only 10 because it was 10 data points. Be very careful. Here's 12 data points. Of course, a fourth of 12 is 3. So what's it tell me to do?
average 3 or 4
Third and fourth
number.
averaged. I like it. So it tells me where the answer is. Then I go take the third and fourth numbers.
What about 2? Just 2.5.
I like it. 62.5. Sweet. So P25, if you made a 62.5 on whatever weird-ass test this is, you would be in the 25th percentile. You only scored higher than a quarter of the people. So when you take the SAT, this is exactly your results. You'll get this back. It tells you for this test, for the group of people who took that test, you scored higher than 25% of them, right? Which is nothing to be excited about. It's better than 10, but what the hell? So on P10, same exact steps.
10% of 12.
Good. 10% of 12 is,
1.2.
that's not a whole number, so I immediately round up.
2.
So I want the second number.
51.
Step 2 is go get the second number. I like it. So P10, 51. Sweet.
When you have to round down, this one is 1.2, and you can only round up if it's above 1.5.
No, it's strictly, it's always round up.
Okay.
And the reason
It
is,
didn't really matter because it was both 51 no matter what.
in this case, yeah. And the last thing in this section is something very interesting. It's called box and whisker plot. Again, not my terminology, but it accurately describes what the hell this thing is going to look like. So let me give you the idea of the 5-number summary. So we already know one way to summarize a list of data is to give me 2 numbers, the mean and
Median.
Standard deviation.
standard deviation. I love it. If I have those 2 numbers, I can tell a lot about the data, right? Here, it's using not mean and standard deviation, it's using percentiles. So if I want a 5-number summary, obviously 2 numbers I definitely want would be the
Standard
The lowest and the highest. I love it. So two of these numbers are low and high. The number right in the middle, of course, should be
Median.
good. The median. Now let me give you some other names. We know it's already P50, but it's also known as, incredibly enough, the second, you're going to love this, the second quartile, Q2. Because what would Q1 do? What would Q1, how far would it go? And what's the first quarter would be up through 25%. So that'd be P25. So the only one I'm leaving out, that's 1, 2, 3. I'm leaving out the fourth one. Of course, that has to be what? Q3, P75, 11. This is called a 5-number summary. Right, because math people are very creative. 5 numbers that summarize your data. I'm like, oh, that's cool, 5-number summary. So what would it be for this data? We've already got several of these. The lowest data point, 51. The highest data point, 150. We already calculated P25, 62 and a half. Let me show you one shortcut you can do. If a quarter of the way in was the third and fourth, P75 would be a quarter of the way in from below. So you just count 1, 2, 3, third and fourth. Do you guys understand that?
You skip the bottom 3 numbers.
The bottom 3.
Skip 1.
Oh, of course I did. Sorry. 1, 2, 3. So third and fourth. Thank you. So if you know P25, if you know how to get to it, you do the same thing from the other side. Now, if you don't like that, just do P75 work. You don't have to do the shortcut. Right? So what would the P75 work look like? 75%, I like it, of 12. 3/4 of 12 is 9. I like it. Cool. And that tells me to do what?
Average it.
Average the 9th and the 10th. Kick ass. So then the 9th and 10th one. So isn't that going to be 12, 11, 10, 9? So it's these two. So it's 1, 2, 3, 4. The third and fourth went in from the end. Some of you guys, I think, see that. P25 is the third and fourth went in from the top. P75 would be the third and fourth went in from the end. I get the same exact place. So that what would that be? The average of 111 and 106.
108.5.
108.5. I like it. So this is 108.5. And then find the median.
50% of 12.
P50.
6 number.
Careful, yeah. You take 50% of 12, you get 6, which tells you to do what?
Average.
Average the 6th and the 7th. Anytime you come out to a whole number on that first step for percentiles, you average that one with the next one. It actually matches exactly with what we do for median, which is what we're doing right now. So the 6th and 7th ones are 1, 2, 3, 4, 5, 6, 7. There.
76.5.
26.5.
70 what?
6.5.
I like that. Okay, so that's the 5-number summary. Let me show you something really cool. If you have your calculator with you, if you put this data in, into list 1, how do I get the mean and all that stuff really quick? I showed you how to check the standard deviation.
1 var.
1 var stats. If you do 1 var stats on this data and you scroll down past the mean and all that, you scroll down, you hit the down button, the last 5 things it has is the 5-number summary. So it's a kick-ass place to go check your work. That is not your work. Your work is this. This is your work. So by now you should know me, that I need to see work. So the last thing I could do with this is to make a visual of it, which is what this is, the box and whisker. And if you're going into teaching at all, high school, stuff like that, they use box and whisker plots all the time. They use box and whisker plots in like educational like comparing colleges to colleges. They do it, the SAT scores, they show a box plot, so forth. So here's what it is. It's really nice and quick. So my 5-number summary goes from 50 to 150 roughly. So I'm going to make a scale. including those things, 50 to 150. So let me go by 10. Why not? 60, 70, 80, 90. Okay. Hopefully your scale would be better than mine. And now here's how silly this is. You're not going to put a dot like you're going to graph it on a number line. You're going to put a line above it. So above 51, you put a line. Above 62 and a half, 76 and a half, 108 and a half, and 150. Is that cool? So lines represent your 5-number summary. Very often, especially with SAT scores from colleges, they like to tell people the middle 50%. Now let's see why that makes sense. Remind me, you don't put this on your picture, but just for our purposes right now, that's the low, that's Q1, Q2, yeah, Q3, and the high, right? So Q3 represents what?
75%.
I know what the value is, but what is it? Be more careful. 75% what? Is below it. Right? So if there's 75% below Q3 and there's how much below Q1?
25%.
How much would be between them? 50. So that's the middle 50. That's what you box off. That's the box from the box and whisker. That box represents the middle 50, and then the whiskers reach out to the extremes, right? The guy that's hated life, and the guy up there that everybody else hates, right? Or girl, I don't know. I can't tell from the data. That's a box and whisker plot, and you're like, well, what the hell else would you call that thing? It's a box with freaking whiskers on it, so you've got to let that go. Really easy to make. You can't beat that. Okay. So that's the last thing they talk about in section 3.4 is box and whisker plots, 5-number summary. So I want to get just a little tiny bit into chapter 4, and then we'll let you guys out a little tiny bit early. So probability, we talked a little bit about how, actually I can't remember how much we talked about it, but the human brain is not exactly hardwired to understand probabilities. And this is why people play the lottery, for example. Now, to be honest with you, I actually play every now and again, just because what the hell? You know, I got $1 I can spare, or $2, depending on which game you want to play. But for example, people that don't pick like 1, 2, 3, 4, because their brain tells them it's not going to be 1, 2, 3, 4. It's going to be something else. So I'll have a higher chance if I don't pick 1, 2, 3, 4. Now that reasoning is right in a very weird way. You're going to pick one number maybe. You got like $1. You can pick one 4-digit number. If you pick 1, 2, 3, 4, are your chances any different than if you picked anything else? You have the same chance. Your brain though is doing one thing right. It's saying that the chance that something else happens is really high. But each individual thing has the same low chance of happening, right? So we don't have an immediate understanding of probability. My little brother, I tell him that I still talk about this to this day. A long time ago, he says, Jeff, you teach statistics, right? I'm like, yeah. He says, do you teach probabilities and all that kind of crap, right? I'm like, yeah. And he says, so it's all crap. You know, either it's is or it ain't. Either it's going to snow or it ain't going to snow. Either I'm going to live or I'm going to die. It's all 50-50. And I said, James, don't become a doctor. I don't want to go in the operating room. Doc, what's my chances? 50-50. You know, I don't want that to be the last thing I hear before I go in. So probabilities, people don't. There's always there's like a homework problem that says there's 2 choices for president. There's a Republican candidate and a Democratic candidate, and of course there's more than that. But let's just focus on that. Does that mean that each one of them have a 50% chance of winning? No, and you've seen that. The last few elections, the last one's a little bit less easy to see. The one before that was a little easy to see who was going to win. I don't care who you're rooting for, you know who's going to win. But it's just that idea, that mistaken idea that if there's 2 things that could happen, they each are a half chance. That's not true. That's not always true. Now, if I have a die and I roll it, if nobody's screwed with that die, what's the chances? Now, let me see if you guys get this. So I have a 6-sided die. Let me be careful in case I have any real geeks out there playing your 20-sided die games. If I have a 6-sided die and I roll it, what's the chances that I'll get a 4?
16.6%.
1 out of 6.
Yeah, the probability I get a 4. And the way that I write that is probability that the value is 4. That's how to read that. The probability that the value I get is 4. You could also say the percentage of the time that the value is 4, because probability is very intimately tied to percentages. So yeah, it's got to be 1 out of 6. Why is it 1 out of 6?
There's 6 sides.
Because out of 6 sides, there's only 1 that matches what I want. So if they sell 7 million lottery tickets, and I buy one of them, my chances of winning are 1 out of 700 million, whatever the hell I just said, right? So it's 1 die side that matches what I want divided by 6. Okay. Now, a perfect thing for probabilities is cards. We're not going to play some complicated card game, so don't freak out. Do you at least know how many suits there are? Is everybody cool with that? I don't want to alienate anybody. You know there's
13
good. There's 13 each suit. The suits are what?
cards. Yeah.
Yeah, the suits are hearts, diamonds. Let me just do this. You got hearts, diamonds, spades and clovers, clubs. Thank you. I'm thinking about Lucky Charms. Your brain just started going. Obviously, I don't trust myself to draw those because I can barely draw a heart. Each suit has 13 cards. 13 cards in each suit, right?
52.
Because there's 52 total. I know that all too well because my older sister would have played random 52 card pickup games. 52 card pickup, pick them up, Jeff. I'm going to hit you. So here's where people go wrong. How many kings are there in a deck of cards?
4.
All right, so what's the probability? If I have a deck of cards and I pick one card, what's the probability that I get a king?
4 out of 52. 4 out of 52.
I don't think I heard anybody say something wrong. Can somebody explain to me why somebody would tell me that this is a mistake? Why somebody would tell me this? What's their reasoning?
Because they're just not in the
There's only a quarter.
Yeah, they're saying there's 4 kings and you want me to get one of them.
Yeah.
But the way they're looking at it then is there's only 4 possibilities for what could happen. No, that's not true. There's 52 things that could happen, right? So the bottom always has to be the total number of things that could happen. If I'm picking one card, there are 52 things that could happen. No jokers in there, right? We threw those out. I'm playing some weird-ass little game. Get the jokers out of there. So it's not that. The probability of a king should be 4 out of 52. I like it because there's 4 kings, 4 chances to get what I just said out of 52 things that could happen. And of course, what does that reduce to?
1 over 13.
1 out of 13. I like it. Reduce, not the percentage. Why does that make physical sense? Can anybody interpret that physically? What do I mean? I interpret this physically. There are 4 cards for every 52. What does this physically mean?
The reduction.
1 king for every suit. I love it. So very often when you reduce a probability, it actually has physical meaning. That's nice. The 1 out of 13 is a whole other way I could have done the problem in the beginning. 1 king for every 13, or 1 king for every suit. I like it. How are we doing so far? All right. Many of you want to keep that a secret. Okay. All right. So from here, if you're decently cool with cards, that would really help me out. And what I sometimes do is I'll provide people with a illustration of a deck of cards to have near them if they need it, right? Because cards are just there for probabilities. It's silly. And any of you play any poker? Yeah. And so, do you understand like pot odds and all? Do you get to that level? Like when to bet and when not to bet, and some situations you got to throw money in based on how much money you've already thrown. And when I say you play poker, do you actually bet? Do you actually gamble? Yeah? No? Okay. Maybe cookies? No. I'm a teacher, so I would not gamble money because I ain't got much of that to begin with. So there's a whole backdrop of probabilities. So when you go into a poker tournament, everybody's got the same chance really of losing a hand in a way, except the reason I like poker better than if I ever go to a casino, I'll never play the freaking slot. Because I don't care how I pull that damn thing or push that damn button, I have no effect on what's happening. But at least in a card game, I can have some skill. The freaking pushing the button, those people scare me. They win lots of money, but they don't care because they've lost more than that through the day. I'm like, man, what a life.
It's usually old ladies who do this lot.
I know, and they're scared. You're away from me. All right. So my point with that was pot odds would be just considering how many options would let me win, how much money have I already put in, is it better in the long run for me to continue? So the last thing I want to talk about then is related to that. When you say this, what does that really mean? What does that mean? So my little brother had a problem because he said if the head and the tail, I flip a coin, what's the chances it's going to be a head?
One.
Chances. 1 out of 2. So 1/2. So chances always have to be between 0 and 100% or 1. With me. What does that really mean? If I flip it once, I'm going to get a freaking head or a tail. So that's why he had problems with the math. But what does it really mean when I say something like this, or when I say probably the head is 1/2? That only makes sense if I do it a lot. So if I flipped a coin 1,000 times, number one, I'm not liking where my life is at. But number two, if I flip a coin 1,000 times, how many heads would I expect to get? 500. If I don't get exactly 500, am I freaking out? No. And this is actually chapter 7 and 8 for us. But I know that if I flip a coin 1,000 times, it should end up around 500, right? And in chapter 8, we actually start to talk about, well, where are those at that describe when something might be wrong with my coin? What would be evidence that, obviously, if I get 100, that's kind of like, whoa, something's wrong with this coin. But what if I get 470? Is that enough evidence that it's weighted one way or the other? Maybe not. We don't know yet. So chapter 8, we're going to talk a lot more about that. Yeah.
So 500 would be the mean,
Good. 500 would be the average. I love it.
and the standard deviation.
Standard deviation would kind of tell me how far out I could go and still be okay. Good. That's the connection we're going to make much later. All right, so that's plenty. We just barely got into section 4.2. So we're going to pick up there next time.